The Pantheon dome in Rome, built in 126 AD, is still the largest unreinforced concrete dome in the world. 1900 years old, no steel, no repairs, no cracks. The Pantheon's dome has no reinforcement. Its weight is entirely supported by the geometry of the compression forces in the concrete itself. The dome is over 43 meters wide at its base. For 1300 years, the Pantheon was the largest dome in the world. From its construction in 126 AD until Filippo Brunelleschi completed the Florence Cathedral dome in 1436, no one built anything larger. The oculus at the top is a design feature, not a defect. It reduces the load and lets rainwater in, which then drains through Roman-designed floor holes that still work today. Modern concrete cracks in 50 years. Once it cracks, water gets in, steel rebar rusts, and the whole structure starts to fail. For a century, engineers wanted to know how the Romans made concrete that outlasts everything we build today. In 2023, a team at MIT finally figured it out. Roman concrete is not a single recipe. It is a class of construction material used across the empire, from Britain to Syria, for over 5 centuries. The Colosseum in Rome, the Pantheon dome, the great aqueducts of Segovia and Nimes. The concrete piers of harbors in Israel, Turkey, and Portugal, some still holding up under the sea. Roman marine concrete at Caesarea Maritima, poured in the 1st century BC, is still there. It has spent 2,000 years being pounded by Mediterranean waves, and it has actually gotten stronger over time. The known recipe was simple: lime, volcanic ash, water, aggregate, small stones, and broken pottery. The volcanic ash, called pozzolana after the town of Pozzuoli near Vesuvius, was the key active ingredient. It reacts with lime and water to form a durable cement. The Romans understood pozzolana was the magic ingredient. They wrote about it. Vitruvius described it in the 1st century BC. In the 1st century AD, workers still went to Pozzuoli by ship to load fresh ash. Roman concrete piers along the Mediterranean coast were poured underwater using pozzolana and lime mortar because the seawater triggered the reaction. Vitruvius wrote that Roman marine concrete solidified more strongly the wetter it got. But volcanic ash alone did not explain why Roman concrete self-heals its cracks. Modern concrete does not self-heal. Once it cracks, the crack widens, water enters, and failure begins. American highway bridges have to be inspected constantly. Some fail after 30 years. For 100 years, scientists studying Roman concrete had noticed something in the samples. Small white lumps, scattered throughout the concrete matrix, millimeter-sized inclusions of pure calcium. They called them lime clasts. The prevailing assumption was sloppy mixing. The Romans had failed to blend their ingredients perfectly, leaving unreacted lime chunks inside the concrete, a minor flaw in an otherwise brilliant material. In 2023, a team led by Admir Masic at MIT looked at those lime clasts more carefully. They took samples from the ruins of Privernum, a 1st century AD Roman city south of Rome. They scanned them with electron microscopes at nanometer resolution. What they found rewrote 100 years of thinking about how Roman concrete works. The lime clasts were not a mistake. They were a deliberate reservoir of reactive calcium built into the concrete. When a crack forms in Roman concrete and water reaches a nearby lime clast, the clast dissolves. The dissolved calcium migrates into the crack. There it recrystallizes as calcium carbonate, a mineral that hardens on contact with air, sealing the crack shut. The concrete literally repairs itself. Masic's team confirmed the mechanism with an experiment. They mixed their own concrete using the ancient recipe. They cast small blocks, they cracked them, they soaked them. 2 weeks later, the cracks had sealed themselves. The self-healing was reproducible. It was not luck. The final piece was how the Romans made the lime clasts in the first place. The team discovered evidence of a technique called hot mixing. Instead of using slaked lime that has already reacted with water, the Romans used quicklime, dropped directly into water. That reaction is violently exothermic. The mixture boils, releases steam, and reaches temperatures well above the boiling point of water. The heat accelerates the setting reactions and, critically, leaves small unreacted lime nodules distributed throughout the mix, the clasts. Vitruvius had described the method in the 1st century BC. The Roman engineer Marcus Vitruvius Pollio wrote the 10-volume De Architectura around 15 BC. It is the oldest surviving architectural treatise in the world. It sat in monastic libraries for 1,000 years. In 1414, an Italian humanist named Poggio Bracciolini rediscovered a copy in a Swiss monastery. It became one of the founding texts of Renaissance architecture. Every classical column, every pediment, every triumphal arch you have ever seen on a modern courthouse or bank is downstream of that one recovered book. Every classical column you see on a modern courthouse is downstream of that one book. But modern scientists had assumed slaked lime was safer and easier and gave better results. For a century they had ignored what he had written down. Since 2023, engineering labs around the world have been racing to develop self-healing concrete for modern infrastructure. The applications are enormous: highway bridges, seawalls, nuclear waste containment vessels, foundations that would last centuries instead of decades. In 2024, a team in the Netherlands poured the first self-healing concrete highway barrier using a Roman-derived recipe. The city of Rotterdam is now casting seawalls with lime clasts embedded. Every civil engineering department in the world is studying it. One of the strangest confirmations came from Roman marine breakwaters at Baiae, on the Bay of Naples. Divers there found 2,000-year-old Roman piers that had actually gotten harder over time. Seawater percolating through the concrete had grown crystalline structures inside the pores, chemically similar to volcanic minerals. The material was still curing after 2 millennia. The Pantheon has been standing for 1,900 years because Roman engineers understood a reactive chemistry we did not understand until 3 years ago. Millions of tourists walk through the Colosseum and the Pantheon every year. Most of them think of Roman engineering as stone and marble. Most of what they are actually walking on is concrete. Concrete that heals itself, concrete that gets stronger under the sea, concrete that Vitruvius wrote about while Julius Caesar was still alive. It is possible we are not more advanced than the Romans in this one specific way. We are still learning what they figured out with wooden buckets and volcanic ash. The Pantheon has one final message. You can outlast steel with the right chemistry. The Pantheon was built as a temple to all the gods of Rome. In 609 AD, it was rededicated as a Christian church. It has been in continuous use for 1,900 years.